Yeah. Hello everyone. I welcome you all to this heat transfer class. Okay. Yeah. I welcome you all to this heat transfer class. In the previous lectures, what we have covered, we have derived and generalized energy balance equation to compute heat transfer to quantify the conduction mode of heat transfer. Then additionally, we also stated its limitation and the we also studied its limitation, and then we have used this generalized energy balance to compute or to quantify the heat conduction mode for one day systems with q dot equal to 0. So here q dot stands for net rate of heat generation, volume or volumetric rate of heat generation, right? So we have studied how to compute, how to use the generalized energy balance to compute one d heat conduction for Cartesian system as well as for radial system. Then in that case, whenever we have also seen something called as a resistance network, which is applicable in case where volumetric rate of heat generation is 0. We studied that in such system we can use the system is analogously, or we can use something called as a resistance network, which basically says which is analogous to the electric resistance concept, in which we have, let's say for example, circuit like this, wherein current I is flowing through this circuit with resistance R1 and R2. Then we can say that this circuit is nothing but an equivalent to current I flowing through a resistance which is R equivalent, which is nothing but the summation of these two things, right? So we have studied for this system, or such a thing is also applicable to heat conduction when we have volumetric rate of heat generation equal to 0. Additionally, we have also studied the overall heat transfer coefficients for radial as well as, so for example here this is the resistance concept which we have studied, right? Additionally, we have also studied the this we have also studied the how to compute a concept called as heat transfer coefficient, and overall heat transfer coefficient, right? So this is dependent on the area through which heat transfer is occurring. For example, here we have a heat transfer coefficient, based on internal surface area, as well as heat transfer coefficient based on outside area, right? So we also studied about this in this class, or in the upcoming classes. What we are going to cover, we are going to here the limitation which we have studied till now was that volumetric rate of heat transfer was equal to 0. So here we are going to relax this condition, and we are going to see how can we quantify heat transfer in system where this volumetric rate of heat generation is not 0. Okay. So now the first system which we are going to consider is conduction with heat generation inside a rectangular slab, right? So here what we have a rectangular slab, right, where the temperature of one of the surface we are maintaining at temperature T1, and the surface of the another the temperature at the of the another surface we are maintaining at some value T2, where we are saying that T1 is greater than T2, right? And then we are also insulating the all the other surfaces, right? So this is insulation. On this side also we are insulating the surface, right? So now why we are doing this, we are doing this to make sure that our system is the heat transfer is going to occur only along this direction, right? This is the direction of heat transfer. So heat is getting transferred, this is direction of heat transfer. So heat is going to get transferred from a surface which is which is at a higher temperature, which in our case is T1, and towards the surface which is at a lower temperature, which in this case is T2. So heat is going to transfer in this direction, and there is no transfer of heat in the y direction, right? So this is clearly a one-dimensional flow of heat, and we are also going to assume the basic assumptions, which is that it is a steady state heat transfer, and the cross-sectional area from the geometry of this system. Clearly, the cross-sectional area at each point is going to remain the constant, right? And we are using a nomenclature. So what is the nomenclature which we are going to use is, we are assuming that the origin of our coordinate system lies at the center of this slab. It will be very clear to you in a couple of slides that why we have chosen this system, this coordinate system. So what we are seeing, that the center of the slab, we are assuming it as is at x equal to 0, and the cooler end or the end with or the surface which has a lower temperature is at x equal to plus L, where L is the half length of the slab, and the temperature and the surface which is at higher temperature is maintained when x is equals to minus L, right? So total, the entirety length of the slab is, we are considering it as a 2L. Okay. So now if you remember, if you remember we can use the generalized heat balance equation which we had derived in first lecture. Since this is a steady state equation, this is a steady state system with only one dimensional flow and cross sectional area is constant, we can use this heat transfer, we can use this generalized heat balance equation to compute it. But prior to that, we have to ask ourselves the question as to what we are interested in calculating. So as I have already always emphasized on, in any case of heat transfer problem, in any heat transfer system, what we are always focused on, we always first try to find what is the temperature distribution or what is the temperature profile inside this system. For this example, so what is the temperature profile inside this system? Let's say, for example, at let's say at x equal to, let's say, 0.2 times L. So we are trying to, let's say this is at this surface. So what we are trying to find is, first question is, what is the temperature here? This is all. This is the first question which we try to answer. What is the temperature distribution and how can you find it? Temperature at a particular x. So if you know the what is the temperature distribution. So now when I say temperature distribution, I say temperature as a function of the coordinate in which heat is occurring. For in this case, this should be x. So we are interested to find what is the temperature as a function of x, right? This is the first point which we always try to find. Then the second point which we try to find is, what is the heat flux? What is the total heat flux or the rate of heat transfer, right? We know that flux or the rate of heat transfer is nothing but area multiplied by the flux of heat transfer. Let me write it here, that rate of heat transfer, rate of heat transfer is nothing but equal to flux of heat transfer multiplied by the area of heat transfer, multiplied by the cross sectional area. So basically these 2 points are same thing. Once we know the flux of heat transfer, we can compute the rate of heat transfer in a converse manner. If we know the rate of heat transfer, we can just divide it by area and we can calculate the heat flux. So these two questions are basically essentially the same thing or similar, right? So we are first, we are what we are interested, we are interested always in trying to find what is the temperature distribution inside the slab. Once we know this temperature distribution, the next question which we will try to answer is, what is the heat flux or what is the rate of heat transfer throughout the system, right? So in order to do this, we jump back to, like I already said, that this is a one dimensional system, steady state one dimensional flow with cross section area is equal to constant. So then we turn back to our heat transfer generalized energy balance equation, which says that dou to t plus q dot by k is equal to 1 by alpha into dou t by dou t, in which case wherein this is nothing but equal to volumetric rate of heat generation inside the slab. This is the thermal conductivity of the material, and this is the thermal diffusivity of the material. Now, since we have said that this system is a steady state system, that means that means temperature is not varying with respect to time. As soon as we say this, we can eliminate, we can let me use a different color, it's a blue. So we can eliminate this because temperature is not varying with respect to time. And the expansion for this dou to t in Cartesian system is nothing but this, right? And since we have said that this is a one dimensional flow, right, this is a one dimensional flow, hence we can also say that these two terms goes back to zero, and this also becomes like I said already, this becomes zero. Hence the overall expression boils down to this expression, right? Overall expression is nothing but this expression. So in the previous case, when there was no volumetric rate of heat generation, we had this term also equal to zero, right? But since now the volumetric rate of heat generation is not zero, we can include that into this expression, and then after rearranging, we end up with this expression. What does this mean? This means that the second derivative. Now note that this volumetric rate of heat generation, this term is nothing but a constant, right? So this is not varying with respect to x, or this is not a function of x. It's just that q dot is the total rate of heat generation, volumetric rate of heat generation inside the system. So in all, this becomes a constant. That means the second derivative of temperature with respect to the position, or with respect to the direction of heat transfer, direction of heat flow, is nothing but a constant, right? Second derivative of temperature with respect to x is a constant, right? When we had this volumetric rate of heat generation equal to zero, in that case this was equal to zero. That is second derivative of temperature with respect to x was equal to zero, and that gave rise to the linear temperature profile, right? But since here we have a second derivative as equal to constant, without even doing any sort of calculation, we can clearly see that the temperature distribution is going to be quadratic in nature, right? So so what do I mean by quadratic? When I say quadratic, that means there is going to be a maxima or minima associated with temperature. So that means that here, so when we had let me write it, let me do it. So when we had a volumetric rate of heat generation equal to zero, then we got a profile like this, a linear profile like this, right? But now, since there is a volumetric rate of heat generation, and the temperature is the second derivative of temperature with respect to the position is constant, we are going to have a like this, a maxima. Either it would be like this, or it would be like this, a minima. Okay, so that's going to be a quadratic in nature. So without even doing any sort of calculation, we see that this is going to be the case. Okay, yeah, yeah. So now this is the temperature profile which we ended up with. Yeah. So this is the temperature profile which we got, that the second derivative of temperature with respect to position is nothing but a constant. In fact, it's a negative constant, right? And when we integrate it out once, we see that this is just a common mathematical integration with c1 with c1 nothing but equal to the constant of integration, right? And then we integrate it out once again, right? So we end up with temperature profile as this quadratic expression, right? So now here we have two constants. So in order to solve this equation, we need two boundary condition, right? So here, if you look at the problem statement here, again we have a boundary condition with in temperature, that temperature when at x equal to minus L is nothing but T1, and temperature at x equal to plus L is nothing but T2. Okay, so this is the boundary condition which we have, that temperature at T1 is going to be just instead of x, you have just have to put, instead of T, you just put T1, and instead of x, you just put minus L, right? So this is the expression which you end up with. And when we simplify this, this is the temperature. The first boundary condition yields this expression for us. Okay, we square it out. Okay, now the second boundary condition, which is temperature at x equal to plus L, is going to be T2, right? So we just put a value of T as T2 and at x as plus L. So we end up with this expression. Okay, yeah. So now what we have two equations. Let me write. These are the two equations with two variables, which are C1 and C2. We should be able to yeah, we should be able to solve this using you can use any method to solve it. So the way I have used this, you just add this to expression, which would eliminate this variable C1, right? So just mathematical manipulation, and you end up with this value of C2. Okay, and then you put this value of C2 into either equation A or equation B. Will end up with uh, you know uh, with this expression, which when you solve gives rise to this. You get that C1 is equal to this, and C1 we already knew. Okay, so that this value of C1 and C2 you put in this expression. Okay, so you'll end up with this temperature profile. So for a simple thing, for a this is the temperature profile which we have, right? So here you see that this is a quadratic in nature. So now okay, let me check. Yeah, so this is quadratic in nature, right? So temperature is quadratic, and then now the question arises as to yeah yeah so then the question arises, let me use yeah so now the question arises yeah question arises that what is the location of this Tmax, right? What and then second question which arises is what is the expression to compute this Tmax, at what location? Let's say for the example, this is the location at which you have Tmax. Now we ask ourselves, what is this Tmax? How do I compute this Tmax using the temperature profile which we derive, right? From this, how do I get it? How do I compute the Tmax? Then second question is, what is the location at which this Tmax occurs? Okay. So those are the two things which we have to answer. So for that, it's just a simple thing. In order to find this x max, what you are going to do is you are going to make dt by dx equal to 0, right? And this happens this is going to happen yeah so dt by dx at x equal to x max is going to be 0. Okay, and using this expression you will get x max, and once you get this x max, you can put it in the you can put this in this expression to compute T max. Okay, so that is what mathematically we have done, right? So in order to find the location of this T max, we assume that it is going to occur at x equal to x max, right? And we take the derivative of the temperature profile, we set it equal to 0, and whenever this happens, that would be our x max. So this is just a algebraic manipulation, right? So let me just tell you what is this. So we just take this temperature profile, and we take its derivative with respect to x, and we set it at equal to 0. So this is what dt by dx looks like. and then when we set it equal to 0, we do some algebraic manipulation, we end up with this x max. The expression for x max is like this, which is t2 minus t1 divided by 2l multiplied by k divided by q max, right? So just in dimensionless form we can write this expression. Okay, so this is very important for you to remember. Okay, and then in order to find this t max, we just put the value of this x equal to x max in this expression. Okay, and then we end up with this value of t max. Okay, this is also very important, right? So now for just simple case, right, here you see we have t2 and t1. So just for simple case, or for example here you see this is a t1 and t2. So now what happens when we have a temperatures at both the surfaces are mentioned as same, are the same, that is t1 is equal to t2. In that case we just have to put t1 equal to t2, and all these complex expressions nullify, and we end up with simple expression, right? Say ts, we just end up with simple expression which I am not going to derive. We end up with this expression that t, the temperature profile comes out to be t is equals to q dot by l square by 2k. This is the simple expression which we end up with, and the location of x max, or the location where we have a maximum temperature, comes out to be at around x equal to 0. This is precisely why we started with this nomenclature, wherein I had with this coordinate system, wherein I had the center of the slab I took as coordinate, or as the origin, where we had x equal to 0, and at the positive end we had a temperature, we had x equal to plus l and x equal to minus l, and the total length of this whole slab was equal to 2l, right? So now this is a homework question for you. What is the temperature profile for this system? So now what we have in here is we have a so we have a slab, whose both the ends are insulated, right? And we are using this x, and this is also insulated. That means at this point dt by dx is equal to 0. Okay, and this is point at x equal to 0, and at x equal to plus l we are having temperature, let's say ts. So now what the question which we are asking is, which you can try it as a homework example, which we can discuss in next class. What is the energy balance for this system? What are the boundary condition? Boundary conditions I've already told, that dt by dx is dt by dx. So let me write this down in a proper way. So boundary condition 1 is dt by dx at x equal to 0 is equal to 0. What is the boundary condition 2? Boundary condition 2 is T, temperature at x equal to plus L is Ts. Then the second, remember that the rate of heat generation, volumetric rate of heat generation is non-zero. Then the third question which we asked is, what is the temperature profile? What are the x max and what are the T max? So let me just try to solve this for the, so we can use, so this is a clearly one dimensional system, steady state system, and cross sectional area is constant. That means we can use our generalized energy balance, which is nothing but dou 2t plus q dot by k is equals to 1 by alpha dou t by dou t. Now since this is a one dimensional steady state system, that means this is equal to 0, and since it's the one dimensional, we can write this as dou 2t by dou x square plus q dot by k is equals to 0. Again, dou 2t by dou x square equals to minus q dot by k. We integrate it out once, we see dou t by dou x is minus q dot by k into x plus c1. Again integrate it out, we see we see temperature is equals to minus q by k x square by 2 plus c1x plus c2, right? Now this is a second order, we have two unknowns, so we need two boundary condition. Already I said boundary condition 1 is dt by dx at x equal to 0 is 0. So that means, so we can use directly this expression, which means minus q dot by k into x plus c1 is equals to 0, which means c1 is equals to, oh sorry, is x will be turned to 0. This means c1 is equals to 0. Okay. And then the second boundary condition is temperature at x equals to plus L is equals to Ts. So that means, so C1 equal to 0, that means temperature becomes, so this term goes to 0, minus q dot by k x square by 2 plus C2. Okay. So now we put this boundary condition into this, we end up with Ts is equals to minus q dot by k L square by 2 plus C2, which gives us value of C2 as Ts plus q dot by k L square by 2. Okay. With this value, we put it in this expression, which basically gives us that temperature is equals to, or we can just put it in this expression also, temperature is equals to minus q dot by k. Let me, we will be putting this in this expression, so which will give us t is equals to minus q dot by k x square by 2 plus ts plus q dot by k L square by 2. Upon rearranging, we get this temperature is equals to Ts plus q dot by k into L square by 2 minus x square by 2. Or we just take out minus here. We end up plus x square minus L square, right? So temperature is equals to Ts minus q dot by 2k L square. Yeah. Minus 1 plus x square by L square. Or in other words, Ts is equals to Qs plus q dot by 2k L square 1 minus x by L whole square, or x square by L square. Okay. Now if you look at this expression and the expression for this case, right? For, I think, yeah, for this case, it turns out to be exactly the same, right? Here also it is this only, and then here also it is same. So let me just copy paste it. Or let me, yeah, paste. This is the expression for this system. Sorry, not this system. Yeah. Copy. Right. And when we had this system, let's say when we had this system, the temperature profile which we got is T is equals to Ts plus this expression I'm writing Q dot L square by 2K into 1 minus X by L whole square by L square. Now this expression is exactly same. This expression is exactly same as this expression. That means these two systems are sort of same thing, and which you can also see here. See, when the temperature profile is like this, that means at x equal to 0, we are reaching a maximum value. That means at this point, at this point, you have dt by dx equal to 0. So the point which is to be highlighted is, if instead of that, instead of this coordinate system, wherein we are saying that the center of the slab we are taking it as x equal to 0, and the two ends are at x equal to plus l and minus l. If we would have taken this x equal to, let's say, 0, this is x equal to l by 2, and x equal to l, you would have end up with different sort of expression. But mathematically, using this coordinate system, this black coordinate system solves, makes the mathematics simplify mathematics. And then by using this coordinate system, you can just use this, just solve this one problem, and this one problem you get it for free. Okay. So basically what we can say is, this problem with this coordinate, with this coordinate axis, is nothing but equal to this problem is nothing but equal to this problem. So this is basically sub part of this problem. That is what I want to convey. Okay. So the homework, or maybe, yeah, so this is, so I've already solved the homework problem, which was this. Okay. Yeah. So I think that is it for today. In the tomorrow's class, what we are going to cover is, we are going to cover the problem set 1. If you have any questions, so we'll do the problem set 1. I'll give you, I'll explain all the details the way we have done it. Okay. So that's it for today. I hope you enjoyed, and I'll hope to see you in the next class. Okay. Just end.